This lesson, we're going to learn how to evaluate absolute value functions and how to solve absolute value equations graphically. The absolute value of x, denoted by the two straight lines around the x, it represents the distance of x from 0, excluding the direction. This is why absolute value is never negative. For example, we say absolute of 3 is 3 because 3 is 3 units to the right from 0. Absolute value of negative 3 is also 3 because negative 3 is also 3 units away from 0. Let's do some examples. When we have absolute of 2 plus 3 times by negative 4, we're going to have absolute of 2 minus 12, which means absolute of negative 10, which is a positive 10. Next question. First, let's highlight the first negative sign into a pink one so we can see what's going on. Then we have to find out what will be the value inside the first absolute value sign, which is absolute of negative 1. And we know absolute of negative 1 will become positive 1. Then negative 4 plus 1 will be negative 3. Then absolute value of negative 3 will become positive 3. But since there's a negative sign in front of it, it becomes negative 3. Next question. Once again, let's highlight the negative sign in front of the absolute sign. Then we know inside the absolute, negative 2 whole thing square is a 4. So we have negative absolute of 4, which is negative 4. That means our answer will be negative 4. The fourth question now. Same thing again, let's highlight the negative sign in front of the absolute sign. And we know the absolute of negative 2 will become a 2. So it will become negative 4. And that means our answer will be negative 4. The last question. First, let's highlight the negative sign in front of the absolute. Then we see absolute of negative 2 will become a positive 2. Then we have negative 2 whole thing square will become a 4. Now we are ready to learn how to graph an absolute function. And through graphing, we're going to solve an absolute value equation. Look at the graph of y equals absolute of x and compare it with two other graphs, y equals x and y equals negative x. Notice that the vertex 0, 0 divides the graph of y equals absolute of x into two distinct pieces. So we say this vertex 0, 0 is the x-intercept, and which is also known as an invariant point. Invariant point is a point that remains unchanged when a transformation is applied. In the case of absolute value, the x-intercept will always be an invariant point because the absolute value of 0 is always 0. So we say when x is less than 0, then the y value will be negative x. We are taking this piece. And when x value is greater than 0, then the y value will be x. Therefore, we can write y equals absolute of x into a piecewise function. First piece is y equals x when x is greater than 0. And the second piece is y equals negative x when x is less than 0. However, we also need to include x equal to 0. So we put equal sign on one of the piece. Let's take a look graphically. So we take this half, and we take this half, combine them, now it becomes our absolute function, y equals absolute of x. Example 1. First, we have the graph y equals absolute of 2x minus 4. Then we're going to rewrite it into a piecewise function. Step 1. We have to graph the function that is inside the absolute sign first, which is y equals to 2x minus 4. In order to graph this line, we're going to identify the y-intercept and x-intercept. So y-intercept, we let x equal to 0. We substitute 0 into the x, we get y equals negative 4. X-intercept, let y equal to 0, then we will get 0 equals to 2x minus 4. That means x equals to 2, which is also our invariant point. That's put it on the graph. So we have the y-intercept of negative 4, we have the x-intercept of 2. Now we make a line. Step 2, we have to take the absolute of the function. That means we are going to flip the graph that is below the x-axis to be above the x-axis. So starting from the invariant point, we know this point here is at negative 2. Now we're going to flip them into positive 2. And this point, step 2, we have to take the absolute of the function. That is to flip the graph to be above the x-axis. So starting from our invariant point, we can see all those points, their y values are negative. So we're going to change them by multiplying a negative 1 to become a positive y value. So negative 2 becomes positive 2. Negative 4 becomes positive 4. Negative 6 becomes positive 6. And negative 8 becomes a positive 8. Step 2. Now we have to take the absolute of the function. That is to flip the graph to be above the x-axis. So let's start with our invariant point. Then you can see all those points are having a negative y values. That means we have to times by a negative 1 to the y values to become positive. That means negative 2 will become positive 2. And negative 4 will become positive 4. Negative 6 will become positive 6. And negative 8 will become positive 8. Now, by connecting all those pink dots and all those positive blue dots, now we are going to have our absolute function. Y equals absolute of 2x minus 4. Step 3, let's rewrite it as a piecewise function. So we say fx equals to, there are two pieces. The first piece is the original y equals 2x minus 4 when x is bigger than 2. Then the next part is we have to multiply a negative 1 to flip all the y value to become positive. So we say negative of 2x minus 4, and when x is smaller than 2. However, we also need to include the 2, so we put equal sign on one of the piece. So we're going to put it on the first piece. That's our piecewise function. Example 2. Now we're going to graph another absolute value function, gx. Step 1, we're going to graph what's inside the absolute value sign first, which means we're going to graph y equals negative 3x plus 8. First, find the y-intercept. That x equal to 0, y is going to be 8. Then we find the x-intercept. We let y equal to 0. Then we get x equals to 8 over 3, which is our invariant point. Next, let's put those two x-intercept and y-intercepts on the graph. As you can see, the x-intercept is not a whole digit. So in order for us to generate a very accurate graph, we need to generate more points. So let's look at this linear relation again. We can see the slope is negative 3, which means negative 3 over positive 1. That means going from the y-intercept, we go down by 3 units, we go to the right by 1 unit to generate another point. And we can repeat the process. Going down by 3 units, go to the right by 1 again to generate another point. So we're going to have those 5 points on. Step 2. Now we have to take the absolute of the function. That is to flip the graph to be above the x-axis. So let's start with our invariant point. Then we're going to flip all the negative y values into a positive y value. So negative 1 will become a positive 1. Negative 4 will become a positive 4. Now, connecting all the positive blue dots and the pink dots, then we're going to have our absolute function. Step 3, let's write gx as a piecewise function. So say gx equals to the first piece, which is the original piece, negative 3x plus 8, when your x value is smaller than a over 3. Next piece is the one that we flipped the negative y value to become a positive y value. So we have to times by a negative sign in front of the function negative 3x plus 8 when x is greater than a over 3. And once again, we also need to include the invariant point. So we put equal sign on one of the piece. So we're going to put on the first piece. Then we will multiply the negative sign into the second piece to have a simplified piecewise function for gx. Example 3. Now we're going to have a quadratic function inside the absolute value sign. So step 1, we're going to graph the function that is inside the absolute value sign, which is the quadratic. Find the y-intercept, let x equal to 0, y is going to be 8. X-intercept, let y equals to 0, fetch out the -1 in front of the x squared, and factor the trinomials, we will get the x-intercept at 4 and -2. Since we have two x-intercepts, that means we have two invariant points. Another crucial point to find for a quadratic function is the vertex. There are two ways to find the vertex. Method 1. X is going to be the sum of the zeros divided by 2, which is the sum of the x-intercepts divided by 2. X is going to be 1. Then substitute back into the function to find the y value, we get y equals to 9. Therefore, the vertex is at 1 and 9. Method 2. We also can use the formula x equals to -b over 2a to find the x value of the vertex. The values of a and b can be found from the standard form. A is the coefficient of the x squared term, which is -1. B is the coefficient of the x term, which is 2. Substitute the values of a and b into the formula, we can get x equals to 1. Then we substitute x equals to 1 back into the equation to find the y value. Then we get y equals to 9. Therefore, we know the vertex is at 1, 9. Now, we're ready to do the graph. We're going to put vertex, x-intercept, and y-intercept on. Then we know parabola is symmetrical, so the other point will be at 2, 8. If we want the graph to be extremely accurate, then we will substitute different x values in to find the y values, such as -3, -1, 3, and 5. Then we can generate 4 other points. After we have the points, then we use a dotted line to draw the original parabola. Then we reflect all the points along the x-axis and draw another parabola. Then we're going to trace the positive region to have our absolute function. Step 3. Now we are ready to write px as a piecewise function. So the first piece is when x is smaller than -2. As you can see, this piece is a reflection of the original blue parabola. So we say the function will be negative times by the original parabola such that x is smaller than -2. The second piece, which is in the middle, which is the original parabola. So the function doesn't change. X value will be in between -2 to 4. The last piece is also a reflection of the original parabola, so we say negative times by the parabola, and the x value will be x greater than 4. Once again, we also need to include the invariant points, which are the x-intercepts, so let's put the equal sign in the middle piece. Finally, let's multiply the negative into the function to have a simplified piecewise function for px. Example 4. Let's graph another absolute value. Step 1. Graph the parabola that is inside the absolute value sign. Find the y-intercept by letting x equal to 0. Then we will get y equals to 0. X-intercept, let y equals to 0. Then add 4 on both sides. Then we take the square root, but remember to have the positive negative sign in front of the square root. Then we will get positive -2 equals x minus 2. Add 2 on both sides of the equation. Then we will get x equals to 4 or x equals to 0. Now we can see we have two invariant points. Next, we have to find the vertex. By looking at this quadratic relation, we know this is already in the vertex form. And if it is in the vertex form, we know the vertex will be at h and k. Therefore, our vertex will be at 2 and -4. Now, let's graph the quadratic function by putting all the points that we know on the graph. In order to have a very accurate graph, I'm going to substitute in the x values of -1, 1, 3, and 5 into the function to find the y values to generate 4 more points that are on the graph. After we have the points that we need, we use a blue dotted line to connect all the blue points. Then we use another dotted line, which is in pink here, to graph a parabola that is a reflection of the original parabola along the x-axis. Finally, now we can trace the blue and pink dotted line that are above the x-axis to graph our absolute value function, hx. Step 3. Let's write the absolute value function hx into a piecewise function. So, as we can see on the graph, there are 3 different pieces. The most left-hand side piece is the original blue parabola. The domain will be x less than 0. The second piece is a reflection of the original blue one, so we have to times by a negative. Then the domain will be 0 less than x less than 4. The last piece, which is the most right-hand side piece, is the original blue parabola, and the domain will be x greater than 4. Once again, we have to include all the possible x values in our piecewise function, which means we need to include the invariant points too. Therefore, in the domain on the second piece, we're going to put in the equal signs, which means x could be 0 and x could be 4. Finally, let's expand the -1 into the square bracket in the second piece. Then we can have our simplified piecewise function, hx. Example 5. Now we're going to learn how to solve absolute value equations graphically. From this equation, the left-hand side is actually one function that's called fx. The right-hand side actually represents another function that's called gx. So when fx equals to gx, this means we are looking for the x values where the y values of those two functions are the same, which means we are looking for the intersection of those two functions, and the intersection is the solution. Step 1. Let's graph the fx, which is y equals absolute of 2x minus 4. So first, we have to graph the linear function, 2x minus 4. We know the slope is 2, the y-intercept is -4. Let's graph the line. After we graph the linear line, found the invariant point, now we're going to flip them. We do not want to have any negative y values. Then, we're going to erase all the negative y values. Now, that's our absolute function, fx. Step 2. Now we're going to graph the gx, which is y equals to 6, which is a horizontal line. Step 3. Now let's identify the intersection points, which is here and here. So we know the point is -1 and 6 and 5 and 6. Now we can make our conclusion. So we know when x equals -1 or when x equals to 5, those two functions, they will have the same y values. Example 6, once again, we're looking for the x values such that the y values of the absolute function is smaller than 3. Step 1, we have to graph the absolute function, 2x minus 5. Before we can find the absolute function, we have to graph the function that is inside the absolute value sign, which is y equals to 2x minus 5. From this linear relation, we know the slope is 2, the y-intercept is -5, then we can graph a linear line. Then, from the invariant point, we're going to flip all the negative y values to become positive y values. Then we have the pink line. After that, let's erase all the negative blue line. Now it becomes our absolute function, 2x minus 5. Step 2, let's graph the function y equals to 3, which is a horizontal line. Now, let's identify the intersection points. So we know the intersection will be at 1, 3 and 4, 3. From this inequality, we know we want the y values of the absolute function smaller than 3. That means we're looking for the region such that the blue line is lower than the red line. Therefore, we know the x value must be in between 1 and 4. Therefore, we say x is element of round bracket at 1 to round bracket at 4. Please note that we cannot use square bracket at 1 and square bracket at 4 because y values can never be equal to 3. Example number 7. Now we have an inequality that has absolute function with quadratic function. Step 1. Let's graph the absolute function. Before we can do this, we have to graph the function that is inside the absolute value sign, which is the quadratic. Let's factor the quadratic in order to find the x-intercepts, and the x-intercept will be at 2 and negative 1. Then, let's find the y-intercept by letting x equal to 0 to substitute into the quadratic function. We will see y-intercept is at negative 2. The next crucial point is the vertex. So one way to find the vertex is to add those two x-intercepts up and divide it by 2 to find the x value of the vertex. After that, substitute x equals to half into the original function to get the y value of the vertex, which is at negative 9/4. Next, let's put all the points on the graph and let's make a parabola. After we have the original parabola, we're going to graph another parabola that is a reflection of the original parabola along y equals x-axis. Then, let's erase the graph that is below the x-axis to get our absolute function of x squared minus x minus 2. Step 2. Let's graph another horizontal line at y equals 4. Step 3. Let's identify the intersection points. So the first one will be at negative 2 and 4, and the second one will be at 3 and 4. And this time, our inequality says our absolute function has to be bigger than 4, has to be higher than 4. That means we want to look for the regions where the blue line is higher than the red line, which is going to be this region here and this region here. So this region is x is smaller than negative 2, and this region here on the right is x is greater than 3. Therefore, we say x is element of negative infinity to negative 2 union 3 to positive infinity.